Typically, when we want to use a flow model, I mean, one thing that I just want to mention here, and then I'm going to drop it, is that we typically do it like in a deep form, right? We always use a deep neural network. And this means that we get our z and then not immediately convert it into x. We get z, we process it into one flow variable, then that flow variable into another one, and so on, right? And if every single of these mappings are invertible, then the whole mapping is going to be invertible, right? So we really don't, I mean, in practice, we're always going to have such an architecture, right? So I'm going to start from some random z, say a Gaussian z sample, and then I'm going to pass it through one flow network. And that network must be invertible, right? I'm going to end up with u1. This is my first flow variable. This is d-dimensional, definitely, because I want f1 to be invertible. And then once I have u1, I can pass it through another function, right? Another model. And that model is going to get u1, give me a new flow variable u2, right? And you can keep on going as much as you want, as deep as you want, till you end up with one variable, which you call it x, right? So this thing that you see here, the sequential change of z into x, this is what we call it flow. But in the literature of generative models, when you say a flow model, you essentially assume that every single of these guys is invertible. Because many things that you know in generative AI, they are doing the same thing. You're going to see for GAN, GAN is doing the same thing, but the difference is that that generator is not invertible, right? So when you say flow, you essentially pre-assume that these functions are all invertible. So this is the whole idea. So a flow is essentially the process which you start from one easy-to-sample latent representation, and you gradually evolve it into a data sample. And the whole idea that we have here is to somehow train all of these models in between, so f1 to fk. We want to train all of them together such that the final output x has a distribution which is somehow looking like the data distribution. And you do know how we can do it. Basically, we are going to, again, do maximum likelihood. Okay? So let me then define the flow process. The flow process is the process of converting z to x. And this is a typical notation people use to just show z to x. And the key point here is that all of the guys here are invertible, so this means that you can get from x back to z, right? And then when you do this, this is what you call it inverse flow process. So you start from z, you go to x, this is flow, and then inverse flow is essentially x to z, right? Now, if you read papers, sometimes people call x to z flow, z to x inverse flow. It doesn't change anything, okay? This is my preference, but you can call the first one inverse flow, the second one flow. I mean, both of them are right. Yeah, this is the point. And the key point here is that for every single of those flow variables, every single guy in between, we can always compute their probability distribution using the normalizing flow or change of variable formula, right? So you do know what is the input distribution. So what is the distribution of the previous? So I minus 1 flow variable, you do know that. And then you divide it by the determinant of the Jacobian of the model itself, so the layer, the particular layer that you're working on. And then you compute everything at ui minus 1. And if you are in the inverse or reverse direction, then essentially you just need to use the reverse flow. So don't get confused. We're going to train the general model together, and then you're going to see everything clear. Yeah? But here, essentially, the thing that I want to tell you is that starting from z, you can gradually change it. As long as you keep everything invertible, then you can get back, and because of that, you can use the normalizing flow formula. Questions? Everybody's clear? No question? Okay. So if you got no question, then essentially a flow-based model is nothing but a network which is going to take d-dimensional input and going to give you back d-dimensional output. That's it, right? So any neural network that you can construct which takes same dimensional input and same dimensional output, plus has this property that you can reverse, so you can get back from the output to input, then this is what we call it a flow model. So again, like the energy-based models, in energy-based models, when we say energy model, that guy itself is not the distribution, right? So you put it in the Boltzmann formula to get the distribution, right? You remember that, right? Now, here again, the flow model itself is not a distribution, right? It's the process or the function which takes one pre-noun, pre-assumed distribution, PZ, and converts it to your data distribution. But the point here is that given that the model is invertible, you are able to compute the distribution. This is very important because you need the distribution when you do maximum likelihood. Everybody's cool? So flow-based model is just one neural network, right? This flow model, this neural network, takes one Z, which is d-dimensional. This is my latent space, and it's going to convert it into the data space. It is not representing by itself the distribution, right? I mean, this output of a distribution cannot be a d-dimensional thing, right? So this is just giving you the process which converts the distribution PZ into the distribution that you want, to the data distribution, okay? So important to pay attention to this point. You don't have directly the distribution. You have distribution using the output of this guy plus the normalizing flow formula, exactly like what we did in the energy-based models. But it's okay, since we can compute it, that's fine, we can use it. Okay, so yeah, here is, I think I want to indicate for the, I don't know, 20th time that this must be invertible. This is very important. So you cannot have non-invertible function as a flow-based model. And typically we start as the latent distribution as a kind of, pre-assumed distribution. Typically Gaussian distribution. This is the best one. Those of you who know information theory, you do know that Gaussian distribution is the most, entropic distribution. So the distribution with the most amount of information or the most amount of confusion. And because of that, starting from Gaussian sounds like the best idea. But anyways, this expression here works for anything, right? So you don't necessarily need to start from Gaussian, but typically we start from a Gaussian. Okay, now, any questions? No question? Okay, so if you want to sample from a flow-based model, how you can do it? Exactly. So this is a very easy thing to do, right? It's not like energy-based models to have the trouble of, doing any sampling algorithm, or like autoregressive model that you need to wait for, autoregressive generation. You don't need that. You just sample from the Gaussian, the latent space, the Gaussian variable. That is easy. You can simply sample it, then you pass it through your network forward. You're going to get your data sample, right? So it's a very easy approach to sample, right? Very effective. Now, what about training it? What if I want to train it? So meaning that, say I have pre-assumed the distribution, so I put the Gaussian distribution here as the latent distribution, and then I consider one neural network here. So I put one neural network which is converting d-dimensional z into d-dimensional x. So I have this network, and I want to train it, meaning that using the samples of data samples coming from data distribution, I want to make those W, the choices of parameters here, such that this network start generating samples from data, right? So I want to do that. The question is how I can do it. And I know that you do know the high-level answer. What is the high-level answer? Maximum likelihood. Great. Okay. Maximum likelihood. You can do nothing more than that, right? So you want to do maximum likelihood. So how we can do it? Well, let's assume that the output distribution is shown by PW. So PW is distribution of X. Again, This PW is not directly hidden inside the network. It's computed from the network, right? Using the normalizing flow formula. But I can compute this distribution. So what I want this guy to be roughly same as the data distribution. I'm going to do maximum likelihood. How can I do it? Say I have one particular sample X. What I want to do, I want to compute the likelihood of this sample, right? The probability of this sample given with my distribution. How can I do it? Okay, I'm going to first pass this X inverse the network. So I'm going to get X using the inverse flow. I'm going to compute the corresponding latent representation. I can do it because my network is invertible, right? Everybody's clear? Now, I have put here under Z as a subscript W. Why I have done this? Exactly. Because Z depends on your network, right? Z is the output of the inverse flow network, right? Meaning that when the weights of the flow network change, then this representation is going to change as well. So this guy is probably the guy who is going to carry us gradients when we are doing the training. This is why I put W here, right? Just to avoid any confusion. So I got my X. This X is a data sample from my data set. I can compute the corresponding latent representation. Since I can do it, I can put it inside the normalizing flow formula, right? To compute its probability given the distribution PW. So it means that the distribution PW at the particular point X is going to be this expression, right? So the nominator is the predefined distribution, the Gaussian distribution that I have, right? And denominator is the determinant of the Jacobian, right? Everybody's cool? Questions? So what I do, I get my sample. I just pass it through the inverse flow. I get my latent representation. Then I put it inside this formula. It's going to give me the likelihood, right? Clear, right? OK. Now, typically we work with log likelihood. So probably we like to have the log form directly. So it's going to be log of the predefined distribution at point ZW minus log of the determinant expression, right? So this is the log likelihood. And at the end of the day, I want to maximize it. Or in other words, I want to minimize its negative value, right? Clear? OK. Let's do it together then. Then let's assume that I have n different samples. This is like a batch of data samples. And what I want to do maximum likelihood using this batch. So first thing that I'm going to do, I'm going to compute the corresponding risk. So we typically like to minimize. So instead of maximizing the likelihood, I'm going to minimize its negative. So this is negative log likelihood. We had the log likelihood in the previous slide, right? So in the previous slide, we showed that the log likelihood was the log of p minus log of determinant. So minus it, it's going to be just change of sign, right? So this is minus log likelihood. This is the expression we had in the previous slide. And we should keep in mind, Z is computed by the inverse flow, right? Everybody's cool? OK. Now, I have a batch of data. The thing that I'm going to do, I'm going to average it over that batch, right? Now, this expression that I'm showing here, so average of some expression of Z, right, over a batch of samples coming from Z, how can I write it down in the compact form? So I'm going to show it, and you tell me if you get it right. Okay? I can write it down in this form. Everybody's clear? Yeah? So that is averaging. We talked about it. When we do averaging, this is estimate of the expectation. So I'm going to replace it with expectation. I have here ZW. And then I write here X distributed with P data, right? The distribution of the data. Okay? And there is no X inside this argument, right? Where is X? ZW, exactly. So it's hidden inside Z, right? So everybody's clear, right? So you have your data sample passing through the inverse flow. It gives you the corresponding Z. That Z depends on your data distribution, right? This is why I write here x distributed by p data, right? Everybody's cool, right? Great. Okay, so the purpose at the end of the day is that we want to minimize this guy, right? And you might wonder how practical that is to minimize this guy. Well, if you think of a very general network, this might be a bit complicated. It's not as complicated as computing partition function. It's not exponentially hard thing, but it could be computationally expensive. That could be the case. This is why we have a specific form of flow design when it comes to practice. But let's break it down, see if we want to just minimize this guy, or in other words, we want to train on a network, what should we do? Okay, so the purpose is to minimize this guy, right? And if I want to minimize this guy, I need to compute the gradient of this whole expression with respect to w, right? I'm going to compute it. I update my w. Then I get a new w. Again, I compute the gradient at the new point. I update and so on, right? This is gradient descent. So the whole thing ends up with computing the gradient. Now, if I want to compute the gradient of the second term, first we start with the second term. If I want to compute that gradient, what should I do? So I'm going to use chain rule, right? And if I use chain rule, it's going to be the gradient of p divided by p, right? Because log, the derivative of log is 1 over argument, right? So that is easy. Then I need to be able to compute the gradient of p, right? Now, I want to compute the gradient of p. If I can compute this guy, I know what is the gradient of the second expression there, right? And if I want to compute it, what should I do? I'm going to use again the chain rule, right? What it would be? It would be first the gradient of p with respect to its argument z, right? Is that a hard thing to compute? What is p, for instance? Is a Gaussian. Now you want to compute the gradient of a Gaussian density with respect to its argument. Is it a hard thing? No. You can easily do that, right? So that guy is very easy to be computed. Then what should I do add next? Is a chain rule. Gradient with respect to z times gradient of z with respect to w, right? So I'm going to add the gradient of z with respect to w. Now, is it a hard thing to compute? No. How can I compute it? Backpropagation. Great. So I can simply backpropagate over the inverse flow, right? Because z was the output of inverse flow, right? X went inside the neural network, z came out, right? Now, if I want to compute the gradient of that output with respect to the weights, I simply use backpropagation, right? This is what you do always in deep learning, right? So that one is quite easy to do. So the second term is easy to be computed. What about the first term? What if I want to compute the first term? The gradient of the first term. What should I do? Of course, I need to again use chain rule, right? Now, I just write it down for you here. I don't expect, we are not going to do it really in practice. In practice, life gets much easier, but I just want to show you the general complexity that we get here. So, if I want to compute the gradient of this guy, I'm going to use this particular formula, and I do not expect that you know it, okay? So you can simply check it in the matrix cookbook, or you can simply do it for small dimensional matrices to see that this is correct. But the whole idea here is that when you take the gradient of log det, then you essentially, that log is going to show up as 1 over det, and that det is going to have some det inside it. So they're going to cancel out. You end up with this expression, x inverse transpose. Okay? So that is going to be quite easy, yeah, in showing. But if you want to compute this gradient, you need to compute the inverse of a matrix, right? And this could be a bit computationally expensive, especially if your matrix is very large. But that aside, right now, we have this formula. So gradient of log det is argument inverse, right? Now, if I want to use this expression in order to compute the gradient of this guy, what should I do? I use chain rule. First, I'm going to compute the gradient of this first term, log det of the Jacobian, with respect to Jacobian, right? And then I multiply it with the gradient of the Jacobian with respect to my parameters, right? So I'm going to write it down this way. So if I use chain rule, the gradient of log det of Jacobian with respect to W is going to be the gradient of log det with respect to Jacobian, which is going to be Jacobian inverse transpose, right? Times the gradient of whatever I have here, which is the Jacobian, right? So I'm going to multiply it with the gradient of the Jacobian with respect to W, right? So now, can I compute this guy? Can I do it? Well, I have Z, right? I have the Jacobian. I can put Z inside the Jacobian expression. I'm going to get the Jacobian matrix, and I inverse it. Whether I can or not, I can. I can do it, but it's going to take me a very long time because I need to inverse a matrix. And inverting a matrix is going to take, cubic order of complexity, right? So that is a hard thing computational-wise, but it's not impossible. What about this guy? Can I do it? I can do it still as well, because the Jacobian, I can write it down in terms of my transform, F, right? And then Z is also coming out of the inverse flow, so I can put it there. I can start writing down chain rules and chain rule and chain rule to end up with the gradient that I want. Okay? So I can do it, but you can again see that this is going to be computationally expensive, because eventually, this matrix is going to have D by D different terms, right? And then you need to just backpropagate inside every single term, right? So you're going to be much more backpropagation as compared to the classic ones, right? So moral of the story here, this second, the whole complexity or the whole computational cost that you're going to pay is going to be for this first term, right? Log det. But this is not going to be something impossible. It's feasible. It's not like the energy-based model, which you cannot do it. In energy-based model, it's exponential to compute such a thing. But here, you don't have a problem in that sense, but it's expensive. It means that it's going to take a long time for every backpropagations you are going to do. And you don't want that typically, because you want to train on a big data. And if you have such a hard time doing one backpropagation, it's going to take forever, right? So everybody's clear? Questions? No question? Great. So moral of the story, this is the hard part, yeah? But it's not impossible. It's still much better than the energy-based models, right? But it's the hard part. Now, we can now write down our training loop for a general energy flow-based model. So what can we do? We can start by specifying one model FW. This model needs to have its corresponding inverse as well, because we need it when we are doing the training. Now, once I set this model to be F, I'm going to initiate it with some weights, and then I get into the training loop. So what do I do in the training loop? Okay, say I sampled one batch of data, so I have n different data samples coming from the data distribution. For every single of them, I'm going to compute the corresponding latent representation, meaning that I use the inverse transform, inverse flow, to just compute the corresponding Z value, right? So every single Z is going to be the corresponding version of, or the inverted version of X, right? And now that I have this guy, I can simply put it inside this expression. I can compute this risk that I want, and I need to do some backpropagation to compute that gradient, right? Now that I computed that gradient, say I have done it for all the samples, I can average those gradients, and I can update my weight, right? Weight updated, I go for the next iteration. I keep on doing till the weight converges. And finally, I give back my flow-based model, right? Now I have the weights. If I want to generate a new sample, I just simply sample from the latent space. I pass it through the same flow network, and I'm going to end up with the data sample. Everybody's cool? You got the idea? So this guy, computationally, sounds easier as compared to the energy-based models, right? And this is why this flow-based model somehow inspired us later for implicit distribution learning, like what we do in GAN, right? Because these guys, I mean, even though GAN was proposed earlier, but GAN, I mean, at that point of time, this flow process was somehow there. And this is one of the key ideas that can help us. Without understanding exactly the distribution, we are able to somehow generate samples. And we're going to see it.